We can represent the configuration of a body frame B in the fixed space frame S by specifying the position P of the frame B in S coordinates, and the rotation matrix R specifying the orientation of B, also in S coordinates. We gathered these together in a single 4x4 matrix T called a homogeneous transformation matrix, or just a transformation matrix for short. The bottom row, which consists of 3 zeros and a 1, is included to simplify matrix operations, as we'll see soon. The set of all transformation matrices is called the special Euclidean group, SE3. Transformation matrices satisfy properties analogous to those for rotation matrices. Each transformation matrix has an inverse such that T times its inverse is the 4x4 identity matrix. The product of two transformation matrices is also a transformation matrix. Matrix multiplication is associative, but generally not commutative. Also analogous to rotation matrices, transformation matrices have three common uses. The first is to represent a rigid body configuration. The second is to change the frame of reference of a vector or a frame. The third is to displace a vector or a frame. To represent a frame B relative to a frame S, we construct the matrix TSB consisting of the rotation matrix RSB, as we saw in previous videos, and the position P of the B frame origin in S frame coordinates. The representation of the S frame relative to the B frame is just the inverse. As with the rotation matrix, the matrix inverse corresponds to switching the order of the subscripts. To change the frame of reference of a configuration, we can use the same subscripts cancellation rule as for rotation matrices. If we know TSB and TBC, we can calculate TSC, representing the configuration of frame C in frame S, by multiplying TSB by TBC. The inverse of TSC is TCS. Just as we followed TSB and then TBC to get to TSC, we can follow TBC inverse and TSB inverse to get TCS. We can also change the frame of reference for a point P in space. Let PB and PS be the representations of the point in the B and S frames. We could naively try our subscript cancellation rule again, but this doesn't work. TSB and PB have a dimension mismatch. To fix this, we simply append a 1 to the end of each vector, making the 3 vector into a 4 vector. This is called the homogeneous coordinate representation of the 3 vector. Finally, a transformation matrix can be used to displace a point or a frame. Consider the fact that any configuration can be achieved from an initial configuration by first rotating and then translating. In this animation, a frame initially at the 0 orientation rotates about a fixed axis omega hat, a distance theta. It then translates according to the vector p, which is expressed in the coordinates of the initial frame t0. Its final configuration is given by t, where the translation and rotation operators are expressed by these matrices. T can be viewed not only as a configuration, but also as the transformation that takes the identity matrix to T. Let's consider a specific example of using a transformation matrix T to move a frame. Our transformation T is defined by a translation of 2 units along the y-axis, a rotation axis aligned with the z-axis, and a rotation angle of 90 degrees, or pi over 2. We will use the transformation T to move the B frame relative to the S frame. The B frame is initially represented by TSB. Since we have 2 frames, we need to know whether the transformation vectors P and omega hat are expressed in the B frame or the S frame. The answer depends on whether T right multiplies or left multiplies TSB. If we left multiply TSB by T, the vectors P and omega hat are considered to be expressed in the frame of the first subscript of TSB, the S frame. Let's animate the transformation T. The rotation axis Z and the translation axis Y, expressed in the S frame, are shown. First, the B frame will rotate 90 degrees about the Z axis of the S frame, and then it will translate 2 units along the Y direction of the S frame. Let's run the animation. And now one more time. Notice where the B frame ends up. We call this new frame B prime. If instead we right multiply TSB by T, the vectors P and omega hat are considered to be expressed in the frame of the second subscript of TSB, the B frame. Also, the order of the operations is reversed. First, we translate TSB, and then we rotate it. Let's animate the motion. Watch how the B frame first translates by 2 units in the y direction of the B frame, then rotates about the z-axis of the B frame. Let's run the animation. Notice that the body's z-axis used for rotation in the second step moved along with the frame during the initial translation. And now one more time. Notice where the B frame ends up. We call this new frame B double prime. In summary, if the transformation t is applied on the right, the vectors p and omega hat are considered to be expressed in the body frame, moving the frame B to the new frame B double prime. If the transformation t is applied on the left, p and omega hat are considered to be expressed in the space frame, moving the frame B to the new frame B prime. In the next video, we introduce our representation of a rigid body linear and angular velocity called a twist.